this lecture. Today I will see ring homomorphism. In my previous video I had seen group homomorphism. I had seen when the algebraic structure preserved, then group homomorphism exists. Today I will see ring homomorphism just as a review. In my previous video of ring theory, I had discussed briefly ring homomorphism. But today I will see ring homomorphism just as a review. Then at first I will see definition of ring homomorphism just as a review. Then I will see how we will find how many ring homomorphism exist from one ring to another ring with examples. This is today's goal of this lecture. This topic is very important, but if you don't see my previous video, at first I will highly recommend you please see the lecture of group theory, also lecture of ring theory. Then today's video would be more colorful, because today's video just as a review part. What is the ring homomorphism? At first I will say definition. Let R and S be rings, and a ring homomorphism is a function who is defined phi from R to S. In group homomorphism it preserves only addition. In ring homomorphism it preserves addition and multiplication. So phi of A plus B equal to here phi of A plus phi of B. This is true for all AB belongs to R, and since it is also preserved the multiplication, so phi of AB equal to phi of A times phi of B. This is also true for all AB belongs to R. And in group homomorphism, 0 map to 0. So in ring homomorphism, multiplicative identity means 1 map to multiplicative identity in S. As for example, consider phi of x equal to 0. This is true for all x belongs to R. Notice this is satisfy property 1 and property 2. But this is not satisfy property 3. I hope my all viewers have understood this ring homomorphism easily. Next I will say, as for example, consider the mapping f from integer to integer, and consider f of x equal to 160x. This is true for all x belongs to integer. Now my question, is it ring homomorphism? Obviously it is group homomorphism, but it is not ring homomorphism. Why? Because notice f of xy equal to 160xy. This is not equal to 160x times 160y. So this is not be ring homomorphism. I hope my all viewers have understood clearly. Okay? Oh well. So since it is group homomorphism, so all group homomorphism Z to Z, how look like? At first think oneself, then see my solution. Since I have seen this is the group homomorphism, so all group homomorphism would be look like f of x equal to nx, where for all n belongs to integer and for all x belongs to integer. Now my question, how look like the group homomorphism from Z to Z? Fx equal to nx, where for all n belongs to Z and for all x belongs to Z. Second question, if you ask how look like the ring homomorphism. Ring homomorphism only possible when n equal to 0 and 1. That means when n equal to 0, 1, then only ring homomorphism possible. That means one ring homomorphism fx equal to 0, this is actually the 0 map, and when n equal to 1, then fx equal to x, this is actually the identity map. Only, even though if we consider -1, then this would be fx equal to minus x. For this also ring homomorphism not possible. That means only ring homomorphism possible fx equal to 0 and fx equal to identity. Okay. Next example, consider one mapping f from Z4 to Z10 such that f of x equal to 5x. For all xy belongs to Z4, f of x plus y, this is equal to 5x plus y, which is equal to 5x plus 5y, and fx plus f of y at modulo 10, because here Z10, this is equal to 5x plus 5y. So this is equal to f of x plus f of y. So this satisfies the group homomorphism property. So this is the group homomorphism. Now I will see, is this ring homomorphism? F of xy equal to 5xy. And notice f of x equal to 5x and f of y equal to 5y. Then f of x times f of y in modulo 10, this is equal to 5x times 5y, which is equal to 25xy, and in modulo 10, this is actually 5xy in mod 10. So this is equal to f of x times f of y. So since f of xy satisfy f of x times f of y, this is satisfied in mod 4 and this satisfy in mod 10. So this is the ring homomorphism. I hope my all viewers have understood clearly. Okay, well. Now I will see how many ring homomorphism possible f from Z4 to Z10. I will count. If there exists homomorphism is such type f of x equal to x, then f of xy equal to would be axy, and this is equal to f of x times f of y, and f of x is ax and f of y is ay. That means this is equal to a square xy. That means when a square equal to a in Z10, then this ring homomorphism possible. And we all of us know, when a square equal to a, then this element is called idempotent element in the ring. So for counting ring homomorphism Z4 to Z10, actually we have to check how many idempotent elements exist in Z10. This is actually rules. How many ring homomorphism exist from a ring to another ring. If F be the ring from Zm to Zn, then actually we have to find the number of idempotent element in Zn. Notice, number of idempotent element For here Z10, for Z10 the rules is 2 to the power D. Here D is the prime divisor of number of prime divisor of 10. Number of prime divisor of 10. Notice here 10 means 2 times 5. Therefore, number of prime divisor is here 1, 2. So this would be 2 to the power 2, this would be 4. So number of idempotent element in Z10 is 4, and this is would be number of idempotent element in Z10 are 1, 0, 1. If 5 be idempotent element, if A be idempotent element, then we all of us know 1 minus A also idempotent element. That means 1 minus 5, which is equal to minus 4. And minus 4 in Z10 means equal to 6. That means 0, 1, 5 and 6 are idempotent element in Z10. So number of homomorphism is 1 f of x equal to 0x, one possibility. Another possibility f of x equal to x. Another possibility f of x equal to 5x. Another possibility f of x equal to 6x. I hope my all viewers have understood clearly number of ring homomorphism from Zm to Zn by idempotent element. Okay, OL. As for example, number of ring homomorphism F from Z30 to Z30. This is actually number of idempotent element Z30, sorry. Number of idempotent element of Z30, and this is equal to 2 to the power prime divisor of 30. Notice 30 means here 2, 15, 3, 5. That means 30 equal to 2 into 3 into 5. Number of prime divisor is 3. So this is equal to 2 to the power 3, and 2 to the power 3 means 8. Therefore, number of ring homomorphism from Z30 to Z30 is 8. Similarly, if we consider number of ring homomorphism from Z3 to F from Z3 to Z3, notice number of ring homomorphism would be 2 to the power prime divisor. Here 3 means only 3. That means 2 to the power 1. This is equal to 2. Okay. Number of ring homomorphism from Z10 to Z5. This is equal to 5 means 5 equal to 5. This is number of ring homomorphism would be 2 to the power 1. This is equal to 2. Okay. So number of ring homomorphism F from Zm to Zn, and this is noticeable if n divide m, then number of ring homomorphism is number of idempotent element of Zn. Okay, OL, which is equal to 2 to the power d, where d equal to distinct prime divisor of n. I hope my all viewers have understood. And these rules is true when n divide m or if f be a mapping from Zm to Zm. The number of ring homomorphism is number of idempotent element of Zm which is equal to 2 to the power d, where d is prime divisor of m. Now consider one mapping f from Z8 to Z4. F from Z8 to Z4, then number of ring homomorphism from Z8 to Z4 is number of idempotent element of Z4. And notice here 4 divide 8. And number of idempotent element of Z4 is 2 to the power prime divisor of Z4, which is denoted as D, and 2 to the power prime divisor of Z4 is actually 4 means 2 square. So there is only one prime divisor. So this is equal to 2 to the power 1 equal to 2. That means number of idempotent elements since here 2. So number of ring homomorphism from Z8 to Z4 is 2. Now I will see. Few minutes ago I have seen number of ring homomorphism from Zn to Zn or Zn to Zm where m divide n. But when the ring homomorphism from Zn to Zm or Zm to Zn, here m does not divide n or m divide n does not matter, then actual rules finding number of ring homomorphism is, if consider Zn to Zm, then at first find the idempotent element in Zm, then possible ring homomorphism this idempotent element times x. Now find the order of idempotent element, which is actually a square equal to idempotent element means a square equal to a, and order of idempotent elements means actually if a is idempotent elements, then since idempotent element in Zm, so a plus a, this is at m times, and this m be the order. We have to find same order element possible is in Zn. Then if same order element possible in Zn also, then we can choose these idempotent element times x. Obviously would be ring homomorphism. Let's see one example when m does not divide n. Then how would be the ring homomorphism? Ring homomorphism F from Z12 to Z30. How many ring homomorphism exist from F from Z12 to Z30? For this is here 30 does not divide 12 and 30 is greater than 12. So at first see the idempotent element of Z30. These are 0, 1, 6, 10, 15, 16, 21 and 25. Now we have to find the order of this element in Z30. Order of 0 is 1. Order of 1 is 30. Order of 6 is 5. Order of 10 is 3. Order of 15 is 2. Order of 16 in Z30 is 15. Order of 21 in Z13 is 10. And order of 25 in Z13 is 6. Then now we have to find, is this order of element exist in Z12? Notice order 1 is 0. There exists no element of order 30 in Z12, no. Order 5. There exists no element of order 5 in Z12. Order 3. Yes. And this is 4. Number of order 3 element is 4. Order 2. There exists order 2 element in Z12. This is 6. Order 15 element, no. Order 10. There exists no element of order 10 in Z12. Order 6, yes. And this is 2. So, number of ring homomorphism is f of x equal to 0x, f of x equal to 4x, f of x equal to, f of x equal to 10x, f of x equal to, for this, f of x equal to 0 times x means trivial. For this, f of x equal to 10x. For this, f of x equal to 15x. And for this, f of x equal to 25x. That means number of ring homomorphism from Z12 to Z30, this is 4. I hope my all viewers have understood this is clearly. Okay, well. Actual formula, the shortcut formula is number of homomorphism, ring homomorphism from Zn to Zn. Actual formula is 2 to the power omega n minus omega to the power n divided by GCD of mn, where these omega n are actually the distinct prime divisor of n. This is actually shortcut rules. Here actually this does not matter, is n divides m or m divides n. This does not matter. This does not matter. Okay. As for example, f from Z5 to Z10, these rules would be 2 to the power omega n. Omega n means omega 10 minus omega to the power 10 over GCD of 5, 10. This is equal to 10 means 2 times 5. So there are two prime divisor, 2 to the power 2. Here omega to the power 10 divided by GCD of 5, 10 means 5. That means this would be 1. So this value would be 2. There exists 2 ring homomorphism from Z5 to Z10. Okay. I will stop here. In my next video, I will discuss ring homomorphism also briefly. But at first, I will highly recommend you please see today's video with pay attention. Okay? See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.